Log on, tune in, find out. Another good idea from Cambridge.
So welcome. So today we have two talks. So first is Steen Ryom-Hansen from Talca, who will tell us about the denominators of Young's semi-normal basis.
Okay, thank you very much for the invitation to come here and speak. So I'll just write the title once again. Young's semi-normal basis. Well, this is not the full title, but anyway. So this is a topic in the representation theory of the symmetric group. I'm going to talk about the representation theory of the symmetric group Sn. So I'll review some basic theory of this representation theory. If K, the ground field, is equal to Q, or any field of characteristic 0, then the situation is very easy. I mean, there's a correspondence between partitions of n, this number, and the irreducible representations. So this correspondence maps a partition lambda to the spec module. So I'll briefly recall the construction of this spec module, and I'll do it in an example. So I'll take, as an example, I'll take n equal to 4. So I need a representation of S4, and I need a partition. So I'll take as my example lambda equal to 3, 1. So I should now construct the spec module corresponding. And now the spec module is going to be a submodule of, it's going to sit inside V tensor 4, where V is a big space that I have explained shortly. And this is in an obvious way a module for S4 by place permutation. So this is a module for S4 by place permutation. Now the Young diagram corresponding to this lambda is this one. 3 boxes in the first row, 1 box in the second row. So I have altogether 2 rows. So for this reason, I take V to be a vector space of dimension 2. So V should now be the span of 2 vectors V1 and V2 over the ground field, and these are the bases. And then the spec module is the span of all ET where T runs through tableau. So I should explain now this map from tableau to ET. ET of course would be a vector in the tensor 4. And I'll do it just also by an example. I'll take as my tableau, I'll take well, a tableau is a filling of the boxes of the partition of the Young diagram with the numbers 1 to 4 in this case. So I take T equal to 1, 2, 3, 4. And then ET is going to be the following element of the central product. It's going to be V1 tensor V1, tensor V1, tensor V2. Because the 1 is in the first row, 2 is the second position, 2 is in the first row. Talking about the first position, I have 3 in the first row, and 4, which refers to the fourth position, is in the second row, like this. And then I should anti-symmetrize with respect to all the columns. Now there's just one column, so I should subtract the V1, the permutation of V1 and V2, the first and the fourth position, because I have here 1 and 4. So it could be 2, V1, V1, V1. And for this expression, I'll use the shorthand 1, 1, 1, 2, minus 2, 1, 1, 1. So this is the construction, more or less, of the spec module. This is with respect to this ET, it's easy to work out the action. 3, 4, for instance, acts in this ET. 1, 2, 3, 4. Well, in the tensor product, the action is by place permutation, and this induces the obvious action in the E's. So this is, I'm going to have to permute 3 and 4. So it's going to be 1 E, 1, 2, 3, and 4. Now these, if I talk about all the tableau, I don't get a basis. So I should talk about only standard tableau to have a basis. S of lambda is the span of ET, where T is standard. And this is a basis. Yeah, all these ET form a basis of the spec module. On the other hand, it's very easy with this action to get from a standard tableau to a non-standard tableau. So if I take the 3, 4, the same one, and act in now in E 1, 2, 3, 4. This is supposed to be an element of S2, 2, another spec module. Then by this action, I get E 1, 2, 3, 4, and this is non-standard. So I need some straightening rules to rewrite this non-standard E in terms of standard. Straightening, rules are needed, and these are the Garnier relations. And these are relations that can be used to straighten a descent that occurs in the columns, in the rows. If there's a descent, if there's a problem in the rows, it can easily be solved just by permuting, because I have here always multiplied by the column stabilizer. So if you interchange 2 elements of a column, you just multiply by a sign. But if you have to interchange 2 elements of a row, you have a problem, and you have to use these Garnier relations. I'll just indicate briefly how they work. So let's say you have 2 columns here. Everything is right here in this column. Everything is also right in the second column. But here I have along this row a problem. I have a descent maybe A more than B, so it's not standard. So I should then consider this part of the first column. I should consider this part of the second column, and I should interchange subsets of this part with subsets of this part in all possible ways. So it's going to be really horrible, and you'll have to repeat this. You'll then get rid of this descent, but there'll be maybe other descents arising, and you have to repeat the process. So you're very happy about these Garnier relations. They are nice but you don't want to use them. So don't want to use them in practice. And for this reason, Young came up with another basis, which unfortunately only works if the characteristic is Q. I mean, so far everything has been valid also over the integers, but now really I'm going to use Q. So Young's basis is beta. You can write with respect to it the matrix of transposition, and you can't do it if you stick to this basis. So Young's basis is also parameterized by standard tableau. And then I'll just write the formula so you see that it really works. That the action of a transposition, say, can be really worked out easily with respect to this basis. I'll just write it. So I take I plus 1, and I act in Ft. So I could two expressions. It's really very simple. You get rho 1 of Ft. You get rho 2 of T prime, where T prime is equal to I plus 1 of C. So I just told you how to act in Tableau. And so I should explain to you what are the numbers rho 1 and rho 2. And rho 1 is, or 1 divided by rho 1 is the radial distance in T between I and I plus 1. So if I, for instance, take 1, 2, 3, 4, and I take I equal to 3, then this distance is 3. And actually say here the distance from I to I plus 1, because there's a sign here. If I change, I mean I get a minus. So I should say from I to I plus 1. And rho 2, there are three cases. Either it's 0 or it's 1, or it's 1 minus rho 1 squared. This is if T is non-standard. This is if T prime is larger than T with respect to the dominance order. There's an order on partitions, the dominance order, which induces a natural order on the tableau, and this is the order I'm talking about here, and this is the other situation. So you can write it down. Okay, so this is but unfortunately you have all those denominators there. Okay, so now I want to talk a bit about how this basis is constructed, because it's going to motivate a bit what I'm looking for. Of course, the basis is due to Young, but James and later on Murphy, found the right way to construct this Ft basis. The construction of Ft due to James, and then later on with a modification by Murphy. This is really the one I'm interested in. James realized that this basis can be constructed using a Gram-Smith process. So Ft is constructed from Et using Gram-Smith. So in order to do Gram-Smith, you need two ingredients. You need an inner product. So the inner product, well, it's the one that you get from the tensor product by restricting down. So it's this. On the tensor product, you have a natural inner product, the one making the monomials normal. For instance, 1, 1, 1, 2, 1, 1, 1, 2 is 1, 1, 1, 1, 2, 2, 1, 1, 1 is 0, just because they are different. So this is a very natural, very easy scalar product here in this tensor product. And if you go down to the spec module, yeah, it's still there, but it becomes much more complicated because you have all those horrible column stabilizers to take into account. But it's easy to define anyway. So you have an inner product, and then you need an order, and of course the order is going to be this dominance order. And this is also where the problem is, because this dominance order is not a total order; it's only a partial order. Yeah, and to make a Gram-Smith, yeah, you need a total order. And you started with the lowest, and then you subtract all the time the projections of your actual element into the lower part. But you need a total order. So of course you can extend this partial order to a total order. But then you have the problem: does the result depend on how you extend? Yeah, so there's actually a little problem here, and this problem can be solved if you have a little more information. Can be solved if one has an operator you have an operator L on the spec module with a self-adjoint with respect to this inner product, and which satisfies the following thing: L of ET is equal to AT ET plus lower terms U less than T A U T E U. So if I have this, I can solve. I can actually make an orthogonal basis. So I just set f of t equal to the product c from minus n to n, L minus c, c different from AT, AT minus c, all this applies to ET. If you do this, you check just formally that ft is going to be an eigenvector for L of eigenvalue ET, AT. I need another condition. I'm sorry, I forgot one condition here that we need for L. Also, the AT, these numbers which are going to be the eigenvectors, eigenvalues, should separate the tableau. So AT, AT should be, if AT is equal to A T prime, then T equal to T prime. I need this second property also. And so they're all now going to be eigenvalues, eigenvectors of eigenvalues, different eigenvalues, so they are orthogonal. So this is the trick. And what are you going to use now as L? We're going to use the Murphy operators. So this is the contribution that Murphy did. So we need to extend a bit this argument, and we need to sort of make another product over all the Murphy operators. So as L, use Murphy operators. And all of this setup reminds us reminds us of a setup in a completely different world. This reminds us of the setup of McDonald theory. It's actually it's completely the same thing that happens in McDonald theory. In McDonald theory, you have reminds us of McDonald polynomials. In the theory of McDonald polynomials, yeah, you study symmetric functions. You have a basis of the symmetric functions, which is the basis of shear function, of the shear functions. You have an order. This is the same order. This is the dominance order because you're talking about here about partitions. The shear functions are also parameterized by partitions, and you have an inner product on the space of symmetric functions, which is the very strange one defined by McDonald. So it depends on two parameters. So McDonald inner product. Yeah, and then you obtain the McDonald polynomials. Yeah, doing this Graham-Smith process. Yeah, and once again you need an operator, and the operator in this situation is going to be Zherednik's operator. So Zherednik operator plays the role of L. So once you have the operator, you can, as Zherednik did, you can calculate the norms of these elements. The bases I construct here, Ft, and the other bases here are only orthogonal bases. They're not orthonormal. So there's an interesting question to determine their norms, and these were, in this case, yeah, the content of the McDonald conjectures. In the case of the Young basis, it was done already, also with this approach here by Murphy some time earlier, and I'll write down the formula. So you see there also there at this place there are some similarities. So I'll just now take a certain specialization of the McDonald polynomials. I'll take the so-called Jack polynomial. So this is a certain specialization of the Jack of the McDonald polynomial. So the norm of this is an expression like this: I less than j. M equals 0 minus k lambda a I lambda j lambda a I minus lambda j plus k j minus I plus m minus m. This is just the formula. In the case of Ftn, and Tn is a float that I'll explain now. So I have my partition. In my order, the lowest tableau is the one that has the numbers 1, 2, 3, 4, so on, filled in increasingly along the columns. I'll do that, but only at one place. This place, for instance, at one removable node, I will put the very last number in. This is going to be my Tn. But the rest is just filled in increasingly along the columns. And for this Ftn, I get the following formula. It's a product along the column of hook lengths. So it's hi minus 1. So it's I running from 1 to k minus 1. Yeah, so running along this column. So this hook length minus 1 times this hook length minus 1, so on and so forth. So I think this is a, if you look at it, if you put k equal to 1 here, you get actually a hook length also there. So they have very similar structures. Of course, the situations are completely different, but I think there's a lot of similarity there. So why not go one step further? In McDonald theory, the next step that was done was to study the base change coefficients between the new basis and the old one. So question: if you write ft in terms of the standard basis a, t, u, e, u, where u is less than t, I mean, this is quite obvious, then obviously e, t is going to be 1. But can we say anything about the other coefficients? Can we say anything about other coefficients? In the case of McDonald, I mean, the McDonald expansion, you can say a lot. I mean, this is the content of the work of Hyman. Yeah? Hyman did the McDonald case. I mean, he proved that there are positivity here. These are polynomials, of course, now in Q and T, and you can prove. He proved some positivity there. So this is one motivation for my work. I mean, just by comparing with this other very similar situation, apparently, although the vector space, of course, is completely different. Another motivation for my work is from the modular representation theory. If you consider now a situation where the root is the field is of characteristic p, and if you assume enough, just for fun, that all hook lengths are less than p squared, assume all hooks are less than p squared, and if you calculate the p-adic valuation of this number, Vp of Vf Tn F Tn, then you get the following thing. You get n r minus n r addable removable. So you should look to the right of the relevant node that you're removing. You should ask along all the places addable. I mean, this number is a number which is very important in the algorithm of in the LLT theory. This is the very basis. This is the very coefficient that appears in their action, in the action that they use on the Fock space. So this is important. So this has something. This has something to do with modular representative theory. So LLT. So this is okay. So I have two motivations here now for studying these coefficients. And then I'll explain now what I have found. So I'll first consider what I call a fat hook partition. Lambda fat hook partition. So lambda is something of this form. So T lambda once again is the tableau that has 1 there, 2 there, and so on and so forth. Now I'll define, generalizing somewhat, this Tn. I'll define now Ti to be, I put I in this position, and the other numbers from 1 to n I fill in increasingly along the columns. 1, 2, 3, 4, 5, so on, so forth. Yeah. This is just a tableau. So I have, of course, here in my form, but I don't want to have it. So I define f Ti. I just write it as fi. Maybe I should put it up there, just for shorthand. And I write e Ti. So I'm interested now in Fn. This is the one I'm interested in. Before I would have written Ftn, yeah, but now I saved a little joke. Okay. So now I need some operator. So assume I, now just another I is a column nx, and assume the numbers of i's column of T lambda, and T lambda is the lowest partition. C I plus 1 C, because this is, I'm talking about T lambda, these numbers will be consecutive. Ci plus 2, Ci plus 3, Ci plus 1, which is the last. So if I have 11, 12, 13, 14, 15, 16, and then I'll have here 10. Yeah, so Ci will be 10. Yeah. Ci plus 1 will be 11, and the last one, Ci plus 1 will be 16. And then I defined Ci to be sigma Ci, comma Ci plus 1 minus 1. So I don't do anything about this one, I take the one before. Minus sigma Ci, sigma I plus 1 minus 2 plus sigma Ci plus 1 minus 3, and this goes on all the way down to plus or minus sigma Ci plus 1 minus and plus 1, where sigma A comma B, whenever A is less than B, is the following permutation, is the following element of the symmetric group. I take A plus 1, I take A plus 1, A plus 2, and I go all the way up to B minus 1 and B. Yeah, so what does this guy here do to this situation? It doesn't do anything about the 16. I never touch the 16. I just start with the 15, I move it there, 10 go there, and so it's a cyclic permutation. Yeah? 15 go there, 10 go there, 11 go there, so on, so forth. And then if I consider the next one, 14 go there, so on. This is how CI acts. And now I can write down and I do it there. Now I'll write down Fn, set Fn to be equal to. I've now used all these operators. I've started with E lambda. This is the E corresponding to the lowest T lambda, the lowest tableau. And then I'll act with the operator corresponding to all the columns that follow. This one, C lambda 2 plus 1, C lambda 2 plus 3, lambda 1. Then I need to do something more. I take now E C lambda 2 plus 2. Oh, that was a tick there. That shouldn't have been there. So I take the one corresponding to this index, and then I go on acting. So it's C lambda 2 plus 2 and so on, so forth up until this one. And I go all the way down. So it's the next one is E C lambda 2 plus 3 C lambda 2 plus 3 all the way up to C lambda 1. And then the last term would be E C lambda 1 C lambda 1. So I'm sorry, I should have written. I mean, of course, this distance is lambda 1, and this distance is lambda 2. So the first column, yeah, is lambda 2 plus 1. So I act in this way. And then the theorem is that Fn is going to be En minus 1 divided by 8 minus 1 times Fn. And this is the first part. And the second part is that all appearing tableau, pole to pole, so say, yeah, ETs appearing in A are standard. Yeah. So the only denominator, yeah, I have here is this one, 8 minus 1. And 8 is, of course, the equivalent from here to here. So there's only one, yeah, there's only one denominator there. Okay. I mean, you might have expected if you hold the very first formula, the formula by Young himself, yeah, you would have expected equivalents appearing there between this point and all of the numbers that are here. I mean, in the beginning they are all there, but then somehow they cancel out. And this formula can also be generalized. So I just it generalizes to arbitrary partitions in a very straightforward way. But I'll just do an example so you see. So the formula, the theorem. Generalizes. I just show the generalization here by taking an example. So I take lambda equal to 5 squared. So 1. So I have the Young diagram like this. 1, 2, 3, 4, 5. 1, 2, 4, 5. 2 and 1. and the one I'm interested in is putting the last number there. So the last number is going to be 13. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then the last number there. So it's almost the lowest, once again, it's almost the lowest, but only I have the last number in some removable node. So this is my Tn. And then Fn is going to be like this. You start with E lambda, the very lowest tableau, and then you act with sigma 4, 7 minus, and then you have a denominator 1. The denominator IRC will be this one and this one, these two bookends. So in this case I have 2, 1 divided by 2, and then some operator, which is the one I had before. So it's F1, and here I'll take sigma 6 sorry, I had to explain. I said this is all based, yeah. The 4, 7 is all based on the standard, on the lowest point. So I should take T, and I should also write down T, the lowest one, T lambda. 1, 2, 3, 4. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. I mean, the ingredients are all, based on what happens in the lowest tableau. So I should say here 4, 7, because I have here 4 and I have here 7, and the operator here is, and the number here 2 is bookend here minus 1. The next one is 7, 13. Because I go from this one to this one, and I subtract F1, 2. And then I need to write down F10 and F12. F10 is just C2, the operator I had before, coming from the second column. And F12 is going to be, you'll see a similar expression as this one. So I take sigma. I'll take first all the products of the column operators. So I'll take C3, C4, C5, and then I'll take sigma 7, 9, C3, C4, C5, and I'll take sigma 7, 11, C5. So I should 7 and 11, and then I operate this last one. So this is the formula, and I think you can easily generalize, write down the general thing. So this was actually what I had prepared. I mean, maybe a bit about the proof. I mean, so just the two ingredients in the proof. I mean, the very first formula, the formula given by Young, act and act and act, which will introduce a lot of denominators that as I said. And then there is the Garnier relation. And the Garnier relation, I mean, in this case, I have to use only one kind of Garnier relation, the one corresponding to one column and a descent in this last row. So here are fewer terms, and they just fit together perfectly with the formula you get by using the Young formula. So I have checked. I have not checked this formula, but I have checked a lot on Maple, and I have checked the, for instance, lambda equal to just cutting here 4, 4, 4, 4, 2, 1. This formula I have. I mean, the formula in this case I have checked. It involves something like 1 million comparisons just to calculate the inner product of the Fn you get with any ET, something like that. I mean, so you cannot expect to go much further, I think, and it works perfectly. And this taking, of course, is done with very formula for the inner product, so it has nothing to do with the proof. You see. So I'm very confident about the formulas I have here. Okay.
Questions?
Can I just clarify this notation here? Well, we say E lambda is your
E lambda?
E lambda is your polytable, whatever.
Yeah, polytable.
But
Yeah.
what is E C lambda 2 plus 2? I see.
Yeah, because now this is a number.
Yes.
Yeah. So this is going to be.
This is an element of the symmetry group, right?
Yeah, because I introduced this notation, yeah, this shorthand.
Yeah.
So whenever I have a number,
Right.
and this number, for instance, here, I agree this is a bit confusing what happens here, but I mean this number now is going to be the last by my setup. This is going to be the last number of the next following column. The one that is there in the lowest row.
Okay.
Yeah, and then I should put it there. This is my formula. I should put it there, and the rest.
All right.
I should put this number, yeah, in this position, and the rest as a filling, increasingly.
All right. Okay.
And then, so I put here also have written C lambda 2 plus 1. Yeah. Okay.
Actually, the second question, or remark, you mentioned this construction by James and Murphy.
Yeah.
Would the same construction done earlier by Justus in 1971?
I disagree. I don't. I disagree. I think he had the operators. That's for sure. Yeah. But I don't think he used them for showing for constructing the. I mean, I don't think he connected them with.
Yeah, I think he introduced the formulas for the idempotence in terms of the what is called Justus-Murphy elements.
Right.
So the formulas the formulas you wrote are contained in his paper. That's what I think. Yeah, it's
I
in
haven't
Russian.
read this paper. Yeah, but.
Yeah.
Well, I think he was. I think really Murphy was the one who connected. I mean, who connected the Murphy the operators, which are maybe also there in other papers. I mean, but I think he was the one who connected them with these.
No, I think that Justus produced the formulas for the idempotence in the what you call Young basis. So in terms of Justus-Murphy elements. So this factorization formulas which you wrote, they are in that paper.
Yeah, okay, I cannot.
I can show you the reference.
I cannot really argue because I must say I have not read it.
Other questions or comments? So then let's thank the speaker again. And then I guess the next talk will be in 25 minutes.